Today we have our very own Val Schmidt. Val holds a Bachelor of Science in Physics from the University of the South and a Master's in Ocean Engineering from the University of New Hampshire. He served as an officer in the U.S. Navy's submarine fleet from 1994 to 1999 and has worked in technical support of oceanographic research for nearly 30 years. Val has led CCOM's research efforts in the use of marine robotics for hydrographic mapping.
Hi, everybody. Wow, an applause even before I get started. It's been a great turnout. Thanks for everybody for coming. I am a little underprepared, I feel like, so I will set the bar a little low just because it's been a crazy week. But my wife is like, if you had more time, your presentation would be shorter, and that's totally true. You also told me that everybody appreciates getting out early. We'll see. We have some kind of special guests here this week. We are hosting NOAA in a training session for the DRIX vehicle, and they're here this week, and they are blessing us by coming and seeing our presentation of all of these hijinks, some of which they've been part of, and so I'm thankful you guys are here. It's great. We have marine robotics program at CCOM, but it's different from most computer science robotics programs in the sense that we're not computer scientists for the most part. Roland is our exception maybe to the rule. We take these guys out to sea and we operate them for the purposes of marine science and hydrographic mapping, often in particular, and figure out the best ways to do that. So a big chunk of the thrust of our efforts, I'm sort of this is the punchline to the whole presentation, really. It's figuring out the balance between autonomy and reliability and automation in these systems and supervision. And what we want to do is make sure that we're operating at a level of risk that we can tolerate. We don't want it to be dangerous. And we want to try to maximize this as much as we can so we can minimize supervision. We got to do that in a whole different slew of environments and situations with different vehicles and different capabilities. And so we try to bump this up with some new technologies and collaborations and new ideas about doing things and automation of things that were never automated before, with software that was never meant to be automated. And we try to reduce the amount that we have to supervise our vessels at sea while they're collecting data. And this hopefully adds to our capability and our efficiency and a whole slew of other things. And sometimes the risk is less. And if we have all of that autonomy, then the supervision goes down and sometimes it gets really low. And that's great because then we don't have to pay attention so much. But sometimes out of the blue during an operation with the same kit, the risk gets really high and that supervision has to go back up. So it's like a spectrum of what we do. We go out and deploy a boat on any given day. Some days it's a set it and forget it. You're bored out of your gourd. And some days it is exciting and everything goes awry. And we have to be prepared for that situation too. So that's the thrust, I think, of all the lessons that we've learned in the last 5 or 6 years. Yeah. So that's my punchline. Supervision big when risk is so sometimes things break and then you need lots of supervision. Okay, so sorting out how is another big part of it. So the mechanics of how we get the vehicles on the ships, how we get the ships out at the sea, how we get the vehicles over the side, how we get them all back safely, how we mitigate failures and all of those things. What do we do to keep it all safe, to make sure that the operators have a good awareness, but the people on deck, a good awareness of their operating environment, but that we can get things back safely on board. Here's an effort on the Thomas Jefferson a month ago. Basile Rose is an operator from X-Blue doing a docking attempt into the DDS there with the DRIX and ultimately waving it off because it just was not a good go. Identifying what things need to be improved. We tried really hard to document everything that went wrong, to make lessons learned from everything that happens, and then systematically try to address those things and make them better. and Andy and KG and Roland and Avery and I and our grad students like pour over what happened, the logs and sorting that stuff out so that we can try to improve things. We work with the manufacturers of this boat and others to give them feedback on how to improve the systems, and we try to help them redesign things where we can. We try to sort out what the best methods are and figure out how we can improve those things. Some of it involves thinking out of the box and figuring out how you mount a painter boom on the side of a ship that you can't weld on and you can't bolt into. So we did it with magnets, and this was our testing efforts to make sure that that would hold. So why do we do this? So we do it to increase the capacity to be able to map and to do marine science. This is Rob explaining this to John. And if you knew these guys, this would, you don't need to know them actually. This is all. We hope that will save time, and we think it will save money, in part because it increases our capacity to do all of these things. I think it'll make it safer by keeping people on big ships instead of on small ships. We think it'll produce better data products sometimes, and we think in some cases it'll produce new data products that we hadn't envisioned before. Because now, with multitudes of vehicles, we hope we can be in more than one place at the same time and get a better synoptic view of the ocean. And we think it'll increase the quality of life of hydrographers. And arguably, maybe that's the best one, because it's a lot better sitting on a big ship with a cup of tea and a cookie, watching the computer screen and your robot boat going back and forth while it's howling wind blowing outside, and your robot boat really doesn't care all that much, and you're nice and comfy, than it is to be on that boat yourself, bobbing around, barfing as you're plugging away at the computer screen trying to make the sonar work. So there's a lot of benefits to hydrographers and to us marine scientists by sorting out all of these other things. Okay, so we have a couple of vehicles, and one of them is ASV Ben. ASV Ben was built by ASV Global, which is now L3 Spirit, acquired by a big defense contractor. It's a Seaworker 4 model vehicle, and it's in the lab out there. And if you've ever wanted to come and check it out and play around and crawl inside it and all that kind of stuff, come see us. You're more than welcome to come do that anytime, and we'll give you the nuts and bolts of it. It's got a whole sensor suite of stuff to sense the environment around it. A lot of these we provide to the operators. Some of them we do some autonomy kind of stuff on board with Ben. That's a constant process to make the perception and the autonomy based on that perception better. It's got a POSM-V, just like any hydrographic, not any, but many hydrographic boats do, which, if you all well know, is a motion sensor and GPS combined together that gives you very precise positioning and attitude so that you can take all the motion of the boat out of your map of the seafloor. It has an EM 2040P multi-beam, which is on a pole down here, which you can't see, but it's in this box somewhere. And then an endurance of like a good full day. So 16 hours at our maximum speed of 5.5 knots. And it's a jet drive, which is like great and bad, right? Because jet drives are like immune to all the lobster pots that we have around here. All the lobster pot floats, so we just like run them over, no problem. But we suck up kelp or sea grass and we're like dead in the water. So we couldn't win. Okay, so I'm going to sort of breeze through some adventures that we've had in the last sort of year and a half since I've given the last CCOM seminar, and just talk about some of the lessons learned that have come out of that and some of the things that we've developed in a bit of an ad hoc way. And those of you who've been involved in this in any great detail are going to be like, but what about this that we did? Or what about that? Or what about this sea story, the other? And like, I know that I have omitted stuff that is important to people in this room, and I apologize for that right from the get-go. We'll be here till next Tuesday if I told all of the stories. But one of the projects that we did in 2021 was an expedition to Thunder Bay National Marine Sanctuary, which is like, this is Michigan and this is Lake Huron. So it's like the upper part of the mitten of Michigan. And this was a collaborative effort between us and the Ocean Exploration Trust. And we had been there before. We had done a mapping effort in 2019, and then we went back in 2021 and added to that mapping effort. And all of the operations for this were out of Rogers City, Michigan. We operated from shore, not from a ship at sea. So we set up kind of our base camp there. This is what our base camp looks like. So we have kind of a control van that we mount antennas on for telemetry out to Ben and power that both from shore, but also with a generator in case the shore power goes out, it's a very important thing, learn the hard way, and operate as far as 20 kilometers offshore with the radio system, so well beyond our line of sight, for all day and sometimes through the night. So this is kind of a view of the inside of what that looks like. We've got a bunch of big screens on the wall for displaying everything, and I'll show you some of that in a bit. There's like 2 VHF radios, one monitoring channel 16 and one for small boat communications with our own support boats. Not uncommon on any other boat to have 2 radios. We have AIS receiver on bend to detect the presence of other boats who transmit AIS signals, but we also have an AIS receiver on the operator station, and we had another small boat that was there supporting, and we had an AIS station on that as well. And through some magic that Roland cooked up and the telemetry systems we had, all of that data from all of those receivers was feeding into the operator station here. So not just what Ben saw, but what we saw on shore and what the 3011, which was that other boat, saw. So this was kind of a new thing for us, like our first dipping our toe into a distributed sensor system where we had situational awareness, not just what was local to Ben, but what Ben's not a big boat, so its view isn't as wide maybe as you would like it to be sometimes. And so that was really kind of neat for us. Let's see, what else is fun there? So we had the Kongsberg Marine Broadband Radio. That's the gadget that passes data between Ben and us over the really long ranges. It's kind of a military grade radio system, but we also had 2 versions of Wi-Fi and UHF. All of that is up on the pole, and a PTZ camera we had in 2019, so that would automatically track Ben as it was running around. So we provide ourselves with as much awareness as possible. And then it looks like we have a big watch team, but we had a lot going on here. So here, Roland is the pilot in this watch team, and Rob Downs is the head of NOAA's Coast Survey Development Lab. And he and a bunch of folks from NOAA came out to help us with this operation and learn from all of that. And they were terrific. And so Rob is kind of the under instruction pilot. Not that he's not a capable and experienced guy on the ocean, but he just didn't know the robotic boat. So that was Roland was there to help him. Steve was a PhD student in computer science who was standing watch and helping out as well. And then Erin is monitoring the survey systems, and she looks totally bored, which is exactly how you want her to be, because that means everything is going really well. And they're like arguing over what to do because a big giant ship is passing right through our survey lane, and they're talking about like what do they do for coal rigs? Do they turn? Do they how are they going to handle that? And of course, Ben only goes 5.5 knots in a big giant ship doing 20 knots. You got to think ahead on those kinds of things. So remember I talked about the spectrum of supervision. You can't supervise anything if you don't have a good telemetry system to the boat. And if you know that the boat's not like sentient and can make all the decisions itself, then you want to make sure that you understand the health of those telemetry systems. And so one of the most important things that we do is we monitor the signal strength of the radio systems and how much data is going through those real time so that we can anticipate when they're likely to go away. When they do go away, you get a sense of why they went away just by the shape of these curves and whether it like falls off like a cliff, you know, something maybe got disconnected versus something that tapers off slowly could be a different kind of a problem. So the robotic boats, both the Drix and Ben, have a middleware called ROS, Robotic Operating System. And it logs data files, all kinds of fields about the health of the system and different parameters of what's going on. And we archive, we're probably the only people who do, we archive all of it. Like every time we go out, we pull all of that data, we store it on servers or in the cloud someplace. We use it for forensic analysis. It's gobs and gobs of stuff. And I thought I would give you an example. So this is a software package. We didn't write it, but it's called Foxglove Studio, and it allows you to look at these ROS bag files. So if you're a hydrographer, you think a bag file is like a topographic map of the seafloor, bathymetric attributed grid, but this is something different. This is like a log file that just happens to have the unfortunate same name, not to be confusing. So this top plot is the the MBR signal to noise ratio as we left the pier and went out on the survey back and forth and then came back. And this is the throughput from that radio, the data coming back from Drix, pretty high, and what goes out to Drix, almost nothing, occasional command from time to time. But this is video streams, remote desktop sessions, a bunch of other stuff. And there's some weird stuff in here that's kind of fun that I thought I would point out. So there's like this funny null that happens on both sides on our transit out. What in the heck is that? So here I've zoomed in a little bit. You can see like there's this big giant, if you're like an acoustics person, you're like, that looks like the near field of a multi-beam transducer. And lo and behold, it kind of is similar to that. It's a multi-path reflection. So the path difference between the two paths is a half wavelength different. They deconstructively interfere and you get a big null in your system. And it's useful to know that might happen because in some circumstances that null may really affect throughput of your data and the continuity. And you can model this and lo and behold, like it kind of looks the same. And then, so let's see. So now we're going to zoom in and I'm going to sort of animate this. So all these plots are kind of linked together. And as this video plays through, you can see the signal sort of bouncing back and forth as we go back and forth on those survey lines. And I've drawn range rings here, roughly 11 kilometers and 14 kilometers on this particular day. And then you can see how it looks like as we go back in. And so then I think I'm going to zoom in and look at maybe this null, I think. That dip. We're going to skip that. So there's a case where you can have three paths interfering. I'm not sure that's actually what's going on here. I think it's a really interesting topic. And there's folks at the Naval Postgraduate School and others in lots of other places around the world who do atmospheric modeling of telemetry systems and radar systems and all that kind of stuff. And this is like an area of research that I am really interested in because our telemetry range with that system on any given day could be 11 kilometers max or 20 kilometers max. And the implication for where you can operate if you're expecting to have telemetry all the time is really big, like huge, like twice the area that you could possibly cover. So modeling this and understanding how it changes from day to day or real time and predicting that, I think is really important. So I think there's like a great graduate student opportunity in sort of sussing a bunch of that stuff out. And we have a kind of a unique kit to do it. Yeah, so that model predicts the same kind of null. And then, so this is the one that I thought we were exploring before. I apologize for that. So here's another dropout. What is going on there? So it turns out that just when that happened, there was, it's a little bit hard to see, but this blue line is an AIS target. So that's a ship transmitting. And that's the ship that passed between us and Bend, but far enough away that we didn't really know it, except it was in the display there. And we even mapped out the shape of the ship with the signals that went by. You can kind of see that it works and it's kind of neat that way. Okay, so another thing that we learned, also the hard way sometimes, is this is the standard view of our operator interface. This is called CAMP, and it gives you a map view with little icons for different vehicles. So this is Ben, this is the NOAA ship 3011. That's the small boat that was out helping us, was doing CPD casts for us. The green up there indicates that we have a telemetry link that turns amber when it goes away for a couple seconds and then red a little bit after that. But the point of this slide is that what you don't see here is that off of this window, there's a big ship whose radar return is there who not transmitting AIS. And so we learned that we need to have two of these displays up. One, that it's good for an operator to kind of micromanage the survey and what's going on and focus on the details of the operation. And another one that's kind of a picture-in-picture maybe kind of thing, where you can zoom out and get a much bigger sense of the view. And so now when we go out on ships, we have two of these. We provide one like this, often for the captain or the officer of the deck on the bridge, so that they can see where they are in relation to land and other ships and where the ASD is. And then often two of these for an operator so that they can have a close-in view, but also have a wider view as well. On this go was the first time that we had integrated a new radar system into Ben, and it's the same radar system that is integrated into DRIX, largely because software we wrote, but the other was what Axel did, which was great in providing the rest of this stuff. But so Axel, I forgot to introduce Axel. So Axel is like the lead software developer for Explu and Robotic, who do the software development for the Drake's vehicle, and he's also visiting helping with the NOAA folks, so I can put it on him as we go. But anyhow, this was also important from a safety point of view. If you've ever played with a marine radar, you know that if you set the range to it, really long distance, so you can see big ships coming in the distance, it won't pick up things well that are close by. So having a dual range system, it's sort of two radars in one. You can set one short and see the small stuff that's nearby, and you can have another one that's far away and see the big ships that are coming that you need to think about. Okay, another thing that we did for the first time is figure out how to operate further away from our base station than our radios would go. And we weren't comfortable doing this without, like, we don't have the collision avoidance system that the DRIX has and the path planning to sort that out safely. So we wanted to do it in a chaperone kind of way. So through some, again, magic that Roland did in the unique architecture that our boat has, it turns out that it's relatively easy to reproduce our entire operator station on a laptop and pair it with AIS receiver and a joystick, like an Xbox controller, and a Wi-Fi bullet so that we could talk to so that's like a little Wi-Fi access point, so we could talk to Ben, and then put all of that on the NOAA launch, and the NOAA launch went out with the DRIX, totally outside the telemetry range of the base station, transfer control from one to the other. And then, sorry, not the DRIX, Ben, I misspoke, but with Ben. And then we went and did the survey for the entire day, and then came back in. Once we came back into range, transferred control back to the shore-based operator station. And we're like, whoa, this is great. We could do this from ships as well. We could deploy an ASV from a ship with a manned launch, and the two of them could go out way distant from the mothership, totally independent, go do their own thing. And the folks on the small launch could sort of chaperone the ASV and do their stuff, and then come back and transfer things ashore. And I think that's a great operating mode, and one that we're going to work on developing further in our stuff. So we have all these telemetry systems up on the mast, and like I said, so these all have like different bandwidths and also different ranges. So at some point you lose the Wi-Fi ones and you still have the MBR, but the Wi-Fi ones can transfer more data than the MBR can. So it's nice to have those. And what we'd really like is a way to send data over across all of those links when they're available for redundancy as much as we can, so that we never even notice when we lose a link, that the data is always coming and there's like no failover time at all. So this is a busy slide, but I'll just say that we've been toying with this gadget that is called a PRP switch. And at a low networking level, it duplicates data, transmits it over telemetry. Well, it doesn't have to be telemetry links. These could be wired links, and then deduplicates it on the other side automatically for you. So it's a way for us to produce great amount of reliability. And like, if you lose one of the streams, you don't even know it because you're getting duplicated data on the other ones. This is a protocol that's used in industrial control. It's not really designed for telemetry links, but we're trying to see if we can't make it work. We tested it on this go in 2021. And what we found, because we never operate all the telemetry streams at once, is that when we did operate them, they interfere with each other. So we were stomping on each other, even though the frequencies are different, they were stomping on each other, and it's another engineering problem that we got to sort out. The problem is here, too much stuff too close. We're in the process of putting another addition onto the mobile lab and automatically rotating those antennas. These are directional antennas to give us better bandwidth, better signal level, and we're going to track Ben as it goes around. A fun project. We added a hailer onto Ben for the first time because we're operating in fog, and you gotta let other boats know that you're out there. And of course, it's one that we could program, so we just played fart signals. So there's nothing in call regs that says you actually have to have a particular tone. We've been working for a while on a prototype CTD winch, and this is a project that is ongoing. We lost our dummy CTD while we were out there during testing. And this is, I think, a great project for a student to work on as well. Kind of a mechanical engineering project and controls project. There's certainly commercial ones that you can buy, well, that people sell. None of them work well, to be honest, due respect to HixBlue and their efforts. But they're not the only people who produce them. But definitely an interesting and challenging problem. So we did cast the old-fashioned way from another boat, except we transferred them wirelessly from the CTD into Ben, just kind of driving up next to it using the telemetry link. So that worked really well. This, by the way, is Tom. He was an undergraduate intern out there helping us. It was really fun to have him. He was super helpful. Sound speed was crazy in the Great Lakes. Like 40 meter per second difference from the surface down below. It was so bad that we were on the phone to John Hughes Clark, like, what is wrong with our data? And he's like, it's not you. And we thought it was us. And he's down there trying to sort out whether or not our multi-beam was loose. But it wasn't us and it wasn't loose. And I watched that all day. It was just really bad environmental conditions. Really difficult. This is a map of sound speed at the surface over time. So we wrote a Python package that can read KML files. That's the format that comes out of Kongsberg Systems, and pulled out all the sound speed, and it's colored by sound speed there. This is the value at the surface, not down through the water column. And you can see how variable it is and how it's changing. Okay, so I'm going to change direction a little bit and talk about the DRIX vehicle. The DRIX was part of an award of a grant from NOAA's Office of Ocean Exploration and a program called the Ocean Exploration, the Ocean Exploration Cooperative Institute. It's like so many acronyms. And it came in the summer of 2021, and it's got sort of very similar sensor suite on the top: LiDAR, radar, again, a Kongsberg Marine Broadband Radio for telemetry, Wi-Fi, GPS. It's got a Kongsberg EM2040 down here. We've also got an EK80 in there and a USBL for tracking underwater vehicles. All of that is in the gondola that's down here on the bottom. It's navigated, it's not labeled here, but in the gondola, there's an INS, the HixBlue fins. And it's unlike the POSM-V, it's an inertial navigation system that only uses one of these two antennas. The other one is actually the AIS receiver. But it gets heading not by measuring the phase difference from two antennas like the POSM-V does, but by measuring the Earth's rotation rate and figuring out from where you are on the Earth, what direction north is, and then sorting it out from there. So it's a much higher grade IMU than the POSM-V in that regard. It's really for underwater vehicles, but a unique kind of gadget. Let's see what else. It's got a camera array as well, AIS antenna. So we're really excited about the DRIX when we first saw it for lots of reasons. We're still excited about it. I don't mean to say that we're not, but the big ones were that its top speed is in excess of 12 knots and its endurance is many days, certainly far, far longer than Ben. So the first time we could operate a vehicle and keep up with the big ship and do it for an extended period of time, or take advantage of the fact that it's got the endurance to transit for a long way to get you into safe harbor if you need to, if the weather's bad, or whatever else. So when we first did tests of it, I think it was in 2018, we went out and did a reference surface. So this was like 14 to 35 meters just off the coast here. And we did that at different speeds, 8, 10, and 12 knots. And we looked at the statistics of these. So this is all RTK navigated. So it's got good navigation, but we basically statistically couldn't tell the difference between these surfaces. The only difference is that at 12 knots, at the higher speeds, the data density is less because you just can't ping fast enough. But everything else looks great. And that was really exciting. Having the sonars down the gondola, like full 2 meters below the water surface where there are no bubbles, really helps a lot. So here's a picture of the DRIX in action. This is in the mouth of the Piscataqua here. That's whaleback light on the top. And this was in 2021. You can kind of get a sense. The wave piercing bow on the front really slices through the water. It's super hydrodynamic. So it's like 7.7 meters long, but only about 0.8 of a meter wide. And and it's really kind of fun to operate, as all the NOAA guys, I think, learned a couple days ago. And then this is us coming back to the pier, and this is the docking system that came with the DRIX that we co-designed. I can't say we co-designed, but we provided a bunch of specs to XBlue and they built for us. It's a little bit unique. I won't go into the details, but these big white panels are LiDAR reflector panels. And although this is a manual docking, when we do this at sea, the DRIX uses those panels to automatically dock itself in. And when it works, it can dock itself better than the rest of us can. Great. So this is kind of a bare minimal operator setup, but this is not really enough, in my opinion. So like you've got maybe a little screen for some camera images, and the HMI, which is the sort of map display for operating, and the telemetry system for looking at all the details, the data streams coming in. But what we do is something a little more elaborate than that. We use that same Foxglove application to stream all kinds of data in real time so that we can see the trends. Because it turns out if you have a number that's changing, it's really hard to follow that and remember what normal is. And if you can see the plot and get a sense of the trend, and if you know the width of the plot, even if you can't see the numbers, you can see that like from far away, and you can see, whoa, what happened there that dropped? That's not normal. And you don't have to be looking up right close at it to see that. So that we find that to be really important operationally. And then, the cameras, it's important to have all those cameras, but we can pass more pixels than we can display. And so we try to turn things off when we can and adjust those to adjust for both the bandwidth and the operating environment. Those big images in the back, this is on the Nautilus and their control van. They have like big giant monitors on the wall, and some of these were repeated up there for other people in the control van to see. And then this is the EK80 sonar. So this is a remote desktop session into one of the computers on the DRIX that operates all the sonars. This is another view of the HMI, and we've laid out a line plan. The Badley data here is courtesy of Paul, and everyone else here over the last 20 years, but it's part of the Gulf of Maine big data set at the university that we have collected over the years. So this is just sort of southwest of the Isle of Shoals. And you can see the DRIX there in the mothership and the survey lines that are laid out there, and we're sort of testing things and all the diagnostics of the vehicle. Get a sense of what all that's like. And then this is that telemetry page with things like oil pressure and engine temperature and battery levels and all that kind of stuff. Kind of give you a sense. And then the DRIX has two cameras, and a color one and an infrared one. Video cameras facing forward, and those are geostabilized. And the camera on this DRIX looks like just like the camera on the other DRIX. For the axle because it's all blurry, and we kind of fix that. And then this is Harper. Harper Umphris is a NOAA Corps officer, but a bunch of you probably know him. He's great. He was out there helping us with DRIX 8 when we were doing surveys. But the thing I wanted to point out is that he's looking at a PTZ camera in the engine room, which is terrific because it allows us to sort of look around in the engine room and see if there's like water in the bilge or oil in the bilge or anything else that's going on. And that's super helpful. Alex came out with us and helped us calibrate our EK80 last summer, and we cooked up this fancy set of fishing poles to do it and dropped the target sphere, and we ended up that not working, and we ended up doing just at the pier, which works really well. And then this is just a great example of what John Hughes Clark is always talking about in terms of mapping water masses in the water column. So we were just happened to have that system on as the DRIX was coming out of the harbor. And here you can totally see the sort of saltwater wedge, classic saltwater wedge, and the standing waves on top of it as we were going out just in the water column data from that sonar system. It's really cool. There he has a new seat, that one's specifically for him. When we were done with this, we had like 100 corrective actions for XBlue, and it's not like the vehicle was falling apart, but we're picky. We wanted things the way they ought to work, but we also have all kinds of ideas about what is needed to make it optimal for a mapping expedition. So then we took DRIX to the Nautilus in Hawaii, and we did 3 cruises on the Nautilus, and I can't even begin to do justice to everything that was done and what was learned. The first one was just an integration and a shakedown cruise. The second one was a tech challenge, which I'll talk a little bit about, which was a collaborative effort between us and folks at Woods Hole and others. And the third one was a coast survey mapping mission around the island atoll of NOAA. And all of those used the DRIX and collaboration and with a bunch of folks in the room. In the workup for this, like integrating this onto a new ship for the first time, it's an effort. It's like there's a lot of practice of towing things if things go wrong, of figuring out how to get the thing over the side and back and practicing that over and over again so everybody knows what their role is and can anticipate what's meant to happen next. So we facilitate all of that when we've gone on a ship. This gives you a sense of the size of the UDS and the DRIX on the deck. It's fine. This gives you a sense of the installation of the telemetry systems way up on the mast, and the operator's control band is in there. And there's more Wi-Fi back on the deck. Part of the installation. We think about things like, what if the gondola won't go up? Because you have to pull the gondola up to set the thing on the deck. And so we work that out with the captain and the crew, how we're going to solve those problems. This is kind of another view of the operating station inside the control van. Maybe we'll skip that one and that one. And then we wrote procedures for deployment, recovery of all of this for the ship. And they kind of look like this, our cartoon version of it. And then like what to do if it all goes wrong, if we have to go get the DRIX, and we write procedures for all of that as well. All kinds of fun things to do. And then go to sea and practice deploying and recovering and deploying and recovering and making sure that it all works and what speed and what heading and all of that stuff. And it's fun. It can be frustrating, but yeah, it's a good go. And then we practice what you do if the DRIX is dead to water and you have to send a small boat out to recover it. There's a tow line here that's paid out, that's broken away from the boat. There's a winch or from the UDS, there's a winch inside the UDS, and the DRIX will get attached to that and then pulled up in. There's a picture of it just in our practice just before we're coming in. You hope you don't have to do it, but sometimes you do. While we were out there, we had a LiDAR malfunction, and we tried to dock the DRIX in an automated way using the LiDAR, not really knowing that the LiDAR was malfunctioning, at least not initially. And it just wouldn't work. Like the DRIX would never track those panels and it would fall away. And we sent data from the DRIX over Nautilus's big giant dome that they transmit all their video stuff back. And my only point of this slide is that, in my opinion, we paid for the cost of that dome by passing that data to Axel and having him and his team look at it and tell us what was going wrong and help us. It was like a couple gigabytes of data that we passed over that link from a ship at sea. And it's so worth it to have those systems. That's my soapbox. But we had a big mishap where the oil filter vibrated loose on the engine, and we basically pumped all of our engine oil into the bilge, which is something you do not want to do. This is not good for an engine. And that was exciting, and that was our first time under duress, having to bring the DRIX back aboard when it wasn't under power, at least on this go. Okay, so the other go was this Tech Challenge cruise. So this one, like we had honed our skills. We had 8 deployments and recoveries, and every LiDAR docking pretty much worked. And we had all kinds of mapping missions. Some of them we did with the Nautilus in tandem. And then we did a bunch of operations with other vehicles, the Mesobot and the NUI vehicles both from Woods Hole. And this is just kind of a panoply of the hijinks from that trip. It was super fun in a beautiful place off of Hawaii. A big chunk of what we were doing was integrating the DRIX with the Mesobot and giving so Mesobot's an underwater vehicle. I don't have a really good picture of the Mesobot for this presentation, I apologize. But Mesobot stands about this high, and Mesobot is a robotic underwater vehicle. Oh yeah, there he is up there, second from the left. Underwater vehicle that samples plankton and does eDNA analysis. Well, it doesn't do the analysis itself, but it filters and samples plankton out of the water column, and then the eDNA sample goes off for analysis. But it's a really amazing system because it can go to very particular depths and stay there, and has a light sensor that looks up. And you might know this, but the biggest migration on the planet is the migration that plankton make from the deep depths of the ocean up and then back down every day on a diurnal cycle. And they do that, we think, based on light levels. And the Mesobot has the ability to track those light levels and track the plankton. But Mesobot doesn't have any sonars, doesn't know where it is. And so we could track the Mesobot with the DRIX and give it all of that sense. So that red line there is the Mesobot coming in and out of the DRIX's multi-beam. And we could check and see, is the Mesobot in that sort of line of plankton there? Is it going to make a sample where it wants to, or do we need to tweak it? In this case, we needed to tweak it. But that was like a really neat thing to be able to do, to be able to verify exactly where the Mesobot was and make sure that it's in the targets that that the scientists are interested to sample. And we could do that with DRIX kind of hovering above it, while the Nautilus is like, 10 kilometers away doing other things. And we passed all kinds of data like CDCast from the Mesobot up to the up through DRIX to us. And then NOAA is kind of a hybrid vehicle that can do seafloor mapping, and they have a really cool technology that they and others have developed called COEX. And the idea is that NOAA maps the seafloor someplace, but they maybe only have an acoustic telemetry link to try to transmit the result of their map back up. And they have a really fancy algorithm that does kind of a low resolution, but prioritized in some special way map of what they're seeing on the seafloor, so that operators over time will start with a fuzzy map that gets more and more clear, and then they can redirect the vehicle on the fly. And we did all of that with the DRIX, providing the communications relay between that vehicle and the boat, while huge separation between those without the ship sitting right on top of it. This is kind of the final map that was made after the cruise of that same seamount, but it was really neat. A big chunk of went into this was a whole bunch of sonar data formats. It's all the nerdy science, but really cool robotics architecture stuff that gets all the points in the right place and reference frames from sonar systems. And a lot of that stuff didn't exist in the robotic operating system. And after this mission, it did. And we learned how to use weather maps to anticipate where the winds were going to be high and we couldn't recover, and where to go and how to hide. And casualty planning when you have multiple vehicles in the water, and thinking about mean time between failures of a system of systems and how that works and the impacts that has on our operations. I'm gonna only say very little. It's probably a good presentation that somebody else can make about this cruise to NOAA, but only to say, that I think it was super successful. It was super challenging because NOAA is like way away from Kauai and the weather did not participate. So they often had to deploy near Kauai, transit 120 odd kilometers or something like that before they could even begin their mapping mission. And I supported from shore, and all I really did was make some endurance models of DRIX and try to give them an idea of how far they could go and at what speeds and what the implications could be, but there's like more work to do there. So that DRIX is getting an upgrade in January. It's going to become the deep water DRIX. For the very first time, Kongsberg has repackaged the EM712 into a gondola that can fit on the bottom of the DRIX. It's pretty exciting. So it'll give us much greater depth capability for the Pacific. These are some pictures that just came yesterday, actually, of that gondola installed on a DRIX in La Ciotat, France, getting tested before it gets shipped out to Hawaii in another few weeks. A big chunk of what we've been thinking about is that whole telemetry thing and how we keep within range, and of course Starlink is seems like an obvious answer to that, right? Like satellite-based system, no practical telemetry limits in terms of range, but some limits in terms of throughput. And this is a plot we made of how much throughput that you can get through a Starlink system, sort of a percentile of time. It's like a very preliminary thing that we're looking at more as a function of weather to see if we can use this for a vehicle that's anywhere on the Earth. Okay, so I'm about to wrap up. There's all kinds of fun and exciting projects that we have in the mix. And some of these might be ones that some of you will be interested in. Some of you are already queued up for a few of them, which is kind of fun too. So as we think about, so there's already algorithms that you can draw a polygon and a vehicle will go and survey that polygon autonomously. Doesn't plan the lines in advance, but we'll go and survey it based on the swath width. That's been done. We've done that. Other folks have done that. Axel has done that as well. But the next logical step to that is to think about what happens before the ship gets on site. So there's like a whole project plan that gets built where somebody draws a really big polygon and says, Thomas Jefferson and all your survey assets, go there and map that. And so the question is, how do you break that big giant area up for the survey assets that you have? What's the most optimal way to do that? How do you plan lines or plan polygons for those systems? How do you get them to finish their surveys at the same time? How do you do that in an automated way with potentially very different depth areas? And some places that you have to go faster or slower than others. So there's a whole interesting thing, I think, to do there. And then part of that maybe is multiple vehicle optimization. So like multi-agent traveling salesman problem planning. So this other people have done. I don't think they've done it in this for this particular application. And there's some nuance to this, I think. But the traveling salesman problem, you're probably familiar with that, right? It's like the very first homework problem that Wheeler gives in his algorithms class. You're a salesman, you have to go to a bunch of cities, and you can only go to each one once, and what's the optimal path to get through that? And you can imagine you're a surveyor, you've completed a big giant survey, a bunch of survey lines, but there's a bunch of holidays all over the place and things that you need to go fix, and you've got kind of the same problem, except each one of those surveylets, if you will, that you got to do, you don't start and end at the same point because there's some line that puts you someplace else. So I've done some work on that and sort of solving a version of the traveling salesman problem for line segments, but I think there's a lot of more interesting things that we could do for that we could tailor it to ocean mapping. It'd be a fun project. Modeling telemetry systems, I talked about that a little bit and try to anticipate and guess how our telemetry systems are going to work, our terrestrial ones. Because I think they're always going to be part of our mix, even in addition to the satellite-based stuff. We got to better understand Starlink and the other satellite telemetry systems that are coming out. Amazon just recently launched or is about to launch their first set of satellites for a competing thing to Starlink. So we understand that some more, both in weather and other kinds of phenomena. Understanding nautical charts. So we've built path plans based on nautical charts before, but with a really rudimentary understanding, really only using the depth information. But it's a different thing to understand that there's a channel and or that there's a buoy and what color the buoy is, or a flashing light and what lights it's flashing and those kinds of things. And so there's an interesting project there, I think, to try to understand those. They're sort of wrapping the concept, all of these concepts of operations in a way that's going to be practical for NOAA, and Airly is going to work on that for part of her thesis. And then another bit also related to telemetry is how we increase the amount of information that's coming over the telemetry links without increasing the data. And that's fundamentally what Jenna, is going to work on, specifically with regard to camera systems and their detections. So that's it. It's 4 o'clock. I'm like 1 minute under. I'll leave you with kind of a fun video from our cruise that the folks at OET made that like none other. And I'm totally happy to take any questions.
You started talking about the spectrum and supervision.
Yeah.
And you're working over a horizon. So you may have some local awareness for your telemetry, but it's still not the same as being there in person.
That's true.
Do you have some ways of judging automatically where the system giving you a heads up if you should be paying more attention to this, or is that not something that's been worked on yet?
It's definitely something we've thought about. Like a great example is, so we routinely operate one vehicle. We rarely ever, maybe never. I mean, XBlue has, but we rarely ever operate more than one. So you can imagine that you have two vehicles out there and you just can't micromanage them both because there's too many of them. And an obvious thing to us is that we've got to put audible alarms in our user display so that when something goes wrong with one and you're focused on the other, your attention is brought to the first one. And it might be a ship that's coming close that it's detected, or maybe it can't find a safe path to travel. It's detected things around it. So some of that stuff is there, but the details of how they're implemented in the HMI and how they're made available to us as operators, we've got work to do. Yeah. I'm glad you asked the question though, because your question made me think of another project that we are remiss on doing. And it's one that's been out there for a long time. And that is that we collect a lot of data, and we've been trying to pull that data across our telemetry link to Larry, who does all of our data processing. Not really true, but and produce data products kind of in real time while the boat's out there. And there's programs like Keras on Board and real-time Chimera, which are commercial products that will do data processing in kind of quasi real time. And we've shied away from those for a couple of reasons. One is that often you end up reprocessing the navigation after the fact anyhow, or you get a more holistic view of the sound speed environment when you can take all the sound speed casts into account. And so we sort of shied away from those software packages as a way to do the processing on the boat. But I think we got to revisit that and come back and think about how we can start producing data products on the boat, and just scrutinizing the products themselves are relatively easy to get over the link. It's the raw data that's hard. And I think that's a great project for someone.
But if we have Starlink, will that be necessary?
So at 4 megabits per second, you're going to be in the same position. You're never going to get KML data files to shore.
We were getting raw data files at the end of each line on the last slide.
It's a 7 or 8 megabit connection that we dial down so that we probably have a good 4 or 5 megabits per second. So there's got to be some of that telemetry link for safety of the boat.
We were operating it all.
But not with Starlink. Like, I don't think so.
That was with the MBR. Yeah. I thought we were assuming that Starlink was going to give us capability like the MBR.
I don't think it's going to give us the throughput that the MBR can give us. I mean, it's certainly it's got global satellite coverage, so it's like totally different in that regard. And I think will give us enough throughput that we can maintain sort of basic safety of the boat. It'll be interesting to see if we can support. If we can support a remote desktop connection over Starlink all the time, like in a reliable way. I don't know when that's necessary. And the sort of stuff that XBlue has put in, of course, like you can't do remote desktop over the Iridium system. So XBlue has put in ways to interact with the sonar that doesn't require so much bandwidth as a remote desktop. So I honestly think that and we can argue about this, but I think there's a real role for doing the processing on the boat and doing the scrutiny of that data and pulling the results off the boat and viewing that afar. And I think that model can work both for ASVs that are at sea and operators that are either on shore or on the ship. But I think it also can work for systems that are on a ship, but the surveyors, the hydrographers are actually on shore and not on the ship. And a similar kind of technology, I think, could enable that. Let me take one back here, someone. Yeah.
So you had mentioned the issues with the whole telemetry thing quite a bit. And I was curious, so it's a bit of a tiered question. So you mentioned that you guys also use 2.4 and 5 gigahertz Wi-Fi to communicate.
Yeah.
But also I think you threw in the Ubiquiti, or were you referring to like a Ubiquiti dish?
Those two systems both are made by Ubiquiti, it turns out, yeah.
And I was curious, like, what is the range for that? Is that just meant to transfer data in close proximity, or how far are you guys able to communicate, like is MBR the primary?
Yeah, so those systems kind of give us a couple of kilometers, not much more than that. A little bit more sometimes, but if the conditions are nice, but rarely much more than that compared to the MBR, which of course it's antenna height dependent, but nominally it's sort of 10 kilometers on a bad day and can be twice that on a good day. It's a huge difference. The benefits of those other systems is just the throughput and having some redundancy of any telemetry system at all.
Okay, very cool. Thank you.
Yeah.
Building on like Larry's comment, is there any way you would approach maybe divvying up your data stream where you send certain things up on Starlink versus certain things on MBR so you can kind of spread the load so to speak, or do you need one to be transmitting it all, or the other to be?
You conceivably could and effectively kind of bond those streams, like make one big pipe out of disparate different ones going in different directions. That's a conceivable thing to do. That's not impossible. I have to think about how we would implement something like that. I mean, there's some low level networking things that can do that, but we might want to be more thoughtful about what those
But
can do.
even like just having, you know, your KML data on one of the streams and then the rest of it on the other stream. I mean, I don't know. anything about
Yeah.
that.
I think it's a good point. When we wrote like our KML Python gadget, KML.py, like it has the ability, for example, to extract backscatter data out of a KML file so that you have just the bathymetry. Kind of thinking, we never really thought that we would push the backscatter through a different link, but just to get to the fundamental stuff that you might want in a hurry, the badly stuff, so that you could send that over a link. So we're sort of thinking in that direction, but we hadn't really gotten around to pushing it over multiple links. Yeah. Yes, sir.
To come back to the discussion about processing on board, I think there's a real case to be made if you go into extremely shallow water and want to push further in so that you have a model that you build that should go certainly along. So is there any plans to do that type of thing?
So we're not doing that on Ben at the moment, but Axel is doing that on the Drix. So he's reading Kongsberg data in real time, gridding it in real time, and I didn't show it, but presenting a course grid to the operator. And he's also implemented a variant of Damien's line planning, like dynamic line planning algorithm. I don't know that you've put in things that would like set a minimum depth into which the vehicle would go if it was going into the, like increasingly shallow water or that kind of stuff, but those are certainly things that we've talked about. Yeah, so some of that stuff exists already and some of it's more to do. Yeah, Alex.
Well, what do you see the future of this in terms of size of the vehicle? What I've seen here on this image, not as big as vehicles. But,
Yeah.
but you can have vehicles that are, you know, essentially autonomous by themselves, don't go on a ship, or vehicles that are much smaller and much easier to pick up and deploy with. But could you comment on that a little bit? I mean, I've answered this.
Yeah.
What's the evolution?
It's a great question. I think when you get to bigger ships, I mean, the big advantage is bigger endurance. And I think like even to make this boat practical, it's really got to be more reliable than a manned vessel, because on a manned vessel, something goes wrong and you can plug the thing back in or reboot the computer or whatever. But all those details have to be taken care of to get the maximum efficiency even out of this vehicle. So that when you do that to a larger vehicle, I think that compounds the problem. Now you've got a system that you have to have noodled over all the possible things that can go wrong and have contingencies for all of those things. And I think that's part of what makes the bigger ones a challenge. There's some things are easier and some things are harder actually on a big vessel. Like in some ways, I think like the law of mass tonnage helps a little bit with a bigger vessel in terms of navigation, but because people tend to stay out of your way, not always, but they tend to. Yeah, I don't know. It's definitely a different navigation problem for the autonomous, like big commercial ships that are trekking across than it is for a small vehicle like these that are operating in coastal waters. I don't know if I answered your question very well.
Sure, it's.
Yes, sir.
So you mentioned that this is collecting eDNA samples as well.
Oh, it's the Mesobot that was doing that. The Mesobot has a sampler. I don't know if we could put up that sampler system on here. We've kind of talked about it at times, but no, it's the Mesobot that has the sampling system for eDNA. So all we did was really give those samples context. Like, were you actually in a place where there's a big plankton layer, or are you not? And was it a plankton layer that's moving? And when the Mesobot lands in that plankton layer, did the plankton layer scatter, which we actually saw one time? So that's like a super important thing to know for the biologists, so they understand their samples. So we could provide context for it, but we didn't actually have the sample. Okay, cool. Yeah.
Deployment and retrieval of this thing.
Yeah.
Open ocean, big waves.
Yeah,
Looks like it could be a challenge.
it
Have you
is.
ever thought about maybe how you could revolutionize doing something like that?
Oh my gosh, every day and every night.
What you coming up with?
Nothing. I mean, like we constantly talk about it, like with the beer at the bar with beers and napkins and whatever else, how to increase the weather window at which you can do this, how you keep it safe. The UDS is big. The DDS is similar to this, but on the NOAA ships, for example, that it's picked up with the davit over the side, you often further up on the side of the ship than certainly not back behind like this is. So it's like a different scenario and a different set of challenges. I think you can see that all that water coming out there, it makes a hump in the back that makes it really difficult for the Drix to steer in. And in particular, when the waves are coming from two different directions, you have like confused seas, and it makes the DDS or the UDS kind of oscillate in a funny way that the Drix has to match in some capacity to steer in there. So we'll continue to work with XBlue to improve this. It's like one of the things that's on our list to do is to work on the algorithms to make this situation better, but it's always going to be a challenge, I think. Yeah, I mean, the Navy sometimes solves it with like designing a whole ship that, back opens up and you just drive little boats in, Yeah, I mean, and that's maybe not practical for NOAA to do. I mean, for other folks with sort of mortal amount of money to spend. But it's definitely a challenge. Yes, sir.
Just curious, do you all have access to the LiDAR sensor data, like live as it comes out, if you want?
We do actually. It can be a little tough to push over the telemetry link in real time, but when we've been troubleshooting that stuff, we have at times displayed it in RViz, which is like 3D environment, to sort of watch and see what we see. And I've certainly recorded it. I had a video, I probably should have showed it from a TJ of Drix coming in, and we could see what it could see and what it was tracking and what it's not. So yeah, you can see that. And it turns out the challenge with this is not, I don't think when the LiDAR is not working, then it's definitely the LiDAR's the problem. But when the LiDAR has been working, it's been tracking those panels just fine. It also tracks everybody's reflective stuff on their life jackets. But it tracks the panels just fine. Those things stand out super bright to that sensor. It's just a matter of matching the motion of a vehicle whose dynamics are different and confused seas and getting cleanly in there. Yeah, it's a challenge. Anything else? Yeah, thank you very much.